investigate neutrino oscillations. But due to the experimental setup, it was being able to measure the neutrinos velocity. A similar experiment to see experiments similar to neutrinos oscillation and measuring neutrinos velocity as well. So when they measured the collapse of the solar neutrinos, was found to be less than the expected one. This problem was solved by scientists by developed theories that suppose that neutrinos oscillate between different flavors. This theory was being proven by two experiments, Super Cameron and Sudbury Neutrino Observatory. Another problem that was resolved by neutrinos flavor oscillation was the atmospheric neutrino problem, when they found that the ratio of neutrinos and electron neutrinos in the atmosphere was less than the half that was being expected. In February 1987, a supernova has been observed in the Large Magellan Cloud 52 kiloparsec away. It was the first time that scientists was being able to observe a supernova with modern astronomical equipment. Two different detectors, Cameron 2 and IMB, was able to detect several neutrino bursts, and from this data it was being able to measure the neutrino's velocity. The velocity was found to be by a factor of 2 times 10 to the minus 9 less than the velocity of light. Neutrinos experiment is the most similar experiment to OPERA. As OPERA originally built in order to investigate neutrino oscillation, but it was being able to investigate to measure the velocity of neutrinos, and in 2005 it was published a paper about this. The velocity of neutrino was found to be by a factor of 5.1 10 to the minus 5 greater than the speed of light, but this value is just consistent with the speed of light less than 1.6 sigma. After are underway in hopes to obtain better results for MINOS in May 2012. Next to Nelson for the scientific preservation.
Thank you. In the science community, there are a lot of rigorous debates about the reliability and the significance of this finding. In our report, we picked out a few publications and a few papers for detailed analysis. However, here we will not have time to go through all the mathematics, but rather we shall just present the conceptual reasoning and the results of some of the most important publications. The first one was produced by Cohen and Gulacho, and is one of the most cited publications by both the scientific and general public media. And they propose that a superlunar neutrino volume and the electron proton pair through a process that is analogous to the strength of radiation and rapidly lose energy through this process. They also derived the equations for the rate of emission and the terminal energy. And in this experiment, the terminal energy corresponds to 12.5 GeV, and any superlunar neutrinos with an energy higher than this value will be depleted. And later, Einstein's team's analysis suggested that the neutrino beam from CERN actually follows an unperturbed energy spectrum, which means there was no decay in the energy. So either opera, which is more likely to be, or Cohen got it wrong. The second paper was produced by Albert from the University of Groningen. Let's first have a look at this animation. This is in the baseline framework reference. Both the photon beam and the satellites are traveling from west to east, which is left to right on the screen. However, in the satellite framework reference, the photon beam is still traveling from west to east because it's faster than the speed of the satellite. However, the baseline is actually traveling from east to west. Since we're using the GPS satellite to synchronize the time distance, we have to consider the special relativity effect due to this relative motion. And he derived the equation and stating that the time of the flight the time of the flight for the photons was actually less than what Opera expected, and the difference is in the form of a first-order Doppler shift. Yes. And a very rough estimation gives a value of 32 nanoseconds for the difference. If given enough data, this value could be even bigger and maybe big enough to challenge Opera's 60 nanoseconds rate. And now I will pass on to Wilson to talk about the paper explaining Opera.
Thank you, Winston. Hi, my section is mainly looking into the theoretical explanation of Opera findings, which we originally naively believed that if Opera results are correct, then is there any mathematics models that we can actually use and apply to explain the data record? So, well, there are some advanced mathematics inside this section, but we're not going to seduce by the mathematics, so we just basically go through the very basic details. So what happened in the basic idea is following, all the methods follow this pattern, okay? We apply a Hamiltonian operator onto the neutrino's wave function, and then let's give an energy, which is the eigenvalue of that. And then we apply a dispersion relationship to relate the energy to the momentum of the neutrino, and therefore the velocity. And after that, basically it's like look at the answer textbook and then match the data back to the theory, like that. Okay. So the first thing we look into is called minimum standard model extension. What it does is basically apply a simplified Lagrangian operator to act onto the neutrino's wave function. So what it gives is two solutions. One of that is the best bit, which is shown on the screen. The blue data are from the Feynman's lab in 2000, which Anton mentioned about. Red dot's Opera, and black dot is the muons. And this generally basically show that there's an energy dependency with the velocity distribution. Yeah, that's it. So that's the best of that method can do. And the second candidate is Lorentz symmetry deformation. So now Lorentz symmetry is very closely related to the spatial relativity because what it suggests is saying under a constant speed, it doesn't matter how fast the speed is going to be, the experimental result should remain the same under a constant speed. So therefore, after Opera results being published, that basically is trying to find some sign of violations and deformations of Lorentz symmetry to explain the data record from Opera. So the idea of the Lorentz symmetry deformation says that the speed limit of the particle is actually energy dependent. So when the particle is in a high energy level, the speed limit actually increases higher than the light. So the particle is able to charge faster from light, but not which is speed limit yet, which is called the preferred frame. However, the preferred frame is theoretically exists, but not actually being observed yet. And also the idea is kind of somewhat similar to the ether idea, which we historically have disproved. So, and the last reason of the quite likely not being true is because this method will modify some coefficient inside the dispersion relation, and that result into the time length will modify in the order of 10 to the 16 meters. So it's, well, if you're desperate to get a hold on pseudo-liminal phenomenon, there are theories to kind of explain it, but it's reasonably unlikely. And now we move on to see the public reaction to the Opera result.
The last thing we looked into in our project was